another 20 minutes or so. Okay. So I have a few more things to actually explain to all of you. So work cells. Work cells is actually a kind of production layout, actually, especially in production. It's actually reorganizing people and machine into groups. So this there's a work cell, and it focuses on a single product or product group of products. For example, this dashboard assembly. Okay, they have cells, and it uses the concept of group technology. So group technology, which actually identify products having similar characteristics for particular cells. That means the cell will actually produce, for example, different models of the same kind of product. Okay, and the volume that you produce must justify cell. I mean, it's a very high volume, and you can actually increase. You can reconfigure. That means you can increase the number of workers when the volume changes. Okay, there is an increased volume. You can actually reconfigure. Right. There are examples after this. The advantages of work cells is will reduce work in process, less floor space required, and also reduce raw material, reduce direct labor. It is because it is having very dedicated group of people. Okay, it's a heightened sense of employee participation because the employee create that work cell together. It will increase equipment and machinery utilization, as well as reduce investment in machinery and equipment. Now, what is the requirement of work cells that you need to actually, before you come up with the work cell, is to identify the family of products that is going to be able to be produced in that work cell. Of course, it is very specialized, so a high level of training is required because it's very, very high, specialized to that particular product group. Okay. It is actually self-contained with its own equipment and resources. And there are pokayoke at each station in the cell. That means there is mistake proving. You will eliminate errors. So this is the idea. That means instead of like this current layout where there are two workers and this is the material and they have their own machine here, it's three. So what happened is that they will actually create a cell. Okay, create a cell. This one example, and then another example is straight line rather than having a straight line flow. Okay, so what they do is actually create a U shape. Workers will have vector access, and they can actually help each other. 4 cross-trained workers were reduced. Okay. And U shape may reduce employee movement and space requirements. Right, let me share you, there are some mathematics involved in stuffing and balancing work cells which you can use to actually balance the work cell. Balance means I want to make sure that the amount of worker A, B, C, content of work is similar. That means if he's working at 50 seconds, then he's also working at 50 seconds. About, okay, 50 seconds. So you don't want A having to work like 80 seconds, this is 50 seconds, this is 40 seconds. So there is no balance. There is no balance of work distribution. Okay, so you can actually, there is a method for actually calculating the balancing work cell. So you need a takt time. Takt time is the total work available divided by units required. Then you can determine the number of operators, workers required, which is the total operation time required divided by the takt time. Takt time normally given by the company. Okay, so if you are producing, for example, the example here, 60 mirrors per day, and your mirror production schedule is 8 hours per day. So from the work balance chart, the total operation is 140 seconds. Okay, 140 seconds. Assembly require 50 seconds, paint and so on. Okay, so this is the content, standard time required for all the amount of work. Okay, so you can actually determine the workers required. Okay, workers required, but of course you cannot have 2.9 workers. That's impossible. Okay, you have to round up. Workers requirement, when you do analysis, if you find that the workers is 3.15, how many workers should you employ? If you find the workers calculation, total operation time, 150 divided by something, suddenly you get 3.15.
4.
Who said 4?
Yes.
Yuma. It's okay. How many workers should I employ? If I calculate and I find 3.15. That's a question. I mean, just testing you, whether you can see the logic or not. Okay, how many workers should you employ? If I do the analysis and find the calculation that workers required is 3.15.
I think it's 4 too.
Okay. It's 4. Do you know how to get, why you get 4? Okay, Fangni, why you say 4? Why is it 4? If I calculate, I find 3.15 and Ho said 4. Okay, why 4? I need to employ 4 workers. Why 4?
Because 3 is not enough. Because 3.15.
Because you have that additional 0.15. Okay,
Yeah,
if you employ 3 workers, who is going to do this? So you need 4 workers. The logic is anything beyond, I mean, it is not rounding up. Sometimes you do calculation 3.15, you round out 3. It is in this real, analysis, I've seen mistakes people do because it is not logic to employ 3 workers when the amount of work required is more than 3.5, 3.6, 3.15. So the logic is that 0.15, who is going to do the 0.15? Okay, so that is, I'm just testing, saying to you, okay. So this is, yeah. Okay, so you'll see this so-called chaku-chaku, this is the work cell. And she will just turn around and chaku-chaku.
Das ist Chaku-Chaku-Linie.
So the worker is actually moving around the cell. At each station, she has the very same thing to do. She just move around, and it will save the time, save the distance. So that's very effective and efficient. But you may think that she is tired, but she's not tired. She's just moving around. Rather than having a straight line and many workers, so this is just one worker. One machine has certain takt time. Takt time is the time taken to do that work. Some are machine operated, some are manually done. So she just push the button. So very competent, very well trained, very skillful, okay, and very accurate. Cannot make a mistake. If you make a mistake, then probably this is a roto used in car. Okay. Okay, Kak? Okay. So I'm going to just finish off this chapter a little bit. We got any questions? Do you have any questions? I think last week we did this what do you call layout, trying to arrange departments, and a little bit of confusion about the cost of calculating the distance travel and the load. Okay, so it's actually a minimization problem. A lot of decision-making problems that you have seen in many of textbooks or problems. We are trying to maximize profit or you want to minimize costs. That is, many of the decision-making tools that we have, and subject to certain constraints, subject to certain conditions. So we have conditions as well as assumptions. Okay, that's very important. So that's why I like you to have analytical thinking, so that when you see a problem, you see a situation, you can try to visualize how to model the problem. Okay, that's one of the most important things. How to model the problem. Okay. So another tool which is actually used in layout is work balance charts. Work balance charts is used to evaluate operations times in work cells, especially if there are more than one workers. Okay. But if there is also one workers, you must balance the time needed for each machine. For example, if you see the other day, there is one worker and, rotating from one steps to another step to another step. So you must make sure that, the time for this first operation is almost equal to the second, almost equal, so that it is balanced. Okay, if it's not balanced, for example, if this take more time than this, for example, this is 50 seconds, this is 20 seconds. So there will be a bottleneck in between the steps. Okay. So why you use for evaluating overtime, and you can help identify bottleneck operations. So if there is bottleneck operation, what you do is you want to redistribute the work elements. I repeat, you want to redistribute the work elements so that the balance, if this 50, this is 20, you want to transfer some of this work to the second. So you reduce this 50 to, for example, 30. Then this becomes 30. So it's balanced. 30 seconds, 30 seconds, 30 seconds, 30 seconds, 30 seconds, 30 seconds is balanced. Okay, that's the most important thing. That's why you see in automotive production line, the worker, there's hundreds of workers. So it's balanced. If one workstation have more work content means more work, and it requires more time, because more work means more time, right? So you cannot balance this, or even machines. Some of the processes have machines. So machine bottlenecks also can be identified. Of course, it requires other approaches. Other approaches, you have to have two machines, or you have to have certain process. So work balance is very important in any processes. Okay, in any, especially in manufacturing. Okay. At the same time, work balance chart it should be flexible, cross-train employees, especially when there are 2 or 3 workers, 2 or 3 employees. So it is cross-train, everybody can do the job. Okay, there is this concept of focus work center and focus factory. Focus work center, big companies, sometimes they create certain work centers within the factory. So that's, for example, that center only produces small parts, or even seat assembly, for example. So that is a work center, or it will become a focus factory if it is big. If it's big, within a factory there is a smaller factory. Okay, so so that's the whole concept. Actually, focus work center and focus factory is trying to actually create separate facility for certain assembly, certain products that you don't want to mix with the other main line. Okay, main products. So it may be focused on certain product line. So you need certain layout and also certain product, new product introduction system as well. Okay. I'm not going to go to detail on it, but just understand within a big factory, there is a smaller factory. For example, in car factory, the stamping shop, stamping press, I will show you a video of this. It is actually a focus factory. It's a focus factory. It's not connected to the main assembly line. It's just producing, the stem parts. Okay, stem parts. Okay. And finally, this repetitive and product-oriented layout. So repetitive, like car manufacturing or what do you call electronic goods. You make televisions. Okay, it's repetitive. Okay, you make air conditions. You make multiple similar products. So repetitive and product-oriented layout. You are organized around products or families of similar high volume, low variety products. But in this case, volume is important because you are trying to have high equipment utilization. Okay. The meaning of high equipment utilization means your machine keep on doing job. Okay, doing work. If not, you are losing money because if you invest in big equipment, then the production volume is low. Then you will lose money. Okay, you need high equipment, high volume for high equipment utilization. And of course, you can use repetitive layout when the product demand is stable, stable enough so that you justify high investment in specialized equipment. Specialized, very specialized. If you go to car factory, it's very specialized. And they run it for few 100,000 products, okay, or years, 4 years to change a new model, okay. And the product is standardized, and also approaching a phase of life cycle that justify investment. I mean, the standardized means that the volume is high. You don't make just one. Compared to job shop, you only just make one spare parts, okay, one component. And also the supply of raw material must be adequate enough and also uniform quality. So imagine a production line, repetitive. So if delivery of, for example, car seats, and the seats is not meeting the requirement, defective, okay, defective, then you cannot install on the line. The line stops. The line stop, 100 workers stop working. 100 staff stop working, you lose. Okay, you lose money because you pay employees to do work. So you have to have uniform quality. Uniform quality means constant good quality parts delivered. Okay. Okay, product oriented is like making what do you call food, canned foods, bottles. So you have your fabrication line which builds component or series of machines, or you can have assembly line. Fabrication means you produce. Assembly line, you put together. This is like car manufacturing or electrical goods. Okay, and you need to actually in assembly line, so that you see balance by moving tasks. Okay, so you move the task so that it is balanced. But in all cases, both fabrication, assembly, both must be balanced so that the time to perform the work at each station is the same. I mentioned just now also, work cells also must have balance. Balance? Balance means one step must have the same time with the next step. Not same, but almost close to each other. Okay, 10 seconds, 11 seconds, 10 seconds, 12 seconds. If it is in 12 seconds, okay. If it is in 1 minute, 60 seconds, 55 seconds, and so on. Okay. So to balance the line, of course, in terms of advantage, product-oriented, like we have seen product strategy, right? So it's low variable unit per cost, low material handling, no work in process, no stocks, with work in process, WIP. Short form is WIP. So those who, if you're in manufacturing, then you will start to, people say WIP, WIP is actually work in process, inventories, okay? Easier training and rapid throughput. But of course, it's not disadvantage. You must have high volume. Disadvantage is that you need high volume. That means it doesn't work on a very small volume. And work stoppages, I mentioned this just now, work stoppage at one point, you deliver defective parts in one station, you stop the line, then the whole operation will stop. So that is mudah ni. Motai nai. Motai nai. Okay. You know, when I was working in Proton, okay, that's what we always do. You know, we try to actually make sure the production line doesn't stop. If a vendor deliver defective parts and result in line stop, there will be penalty. That means there will be fine. You know, penalty. You have to pay for every minute stop. 1 minute line stop, the vendor pays some X dollars of compensation, penalty, because they deliver bad parts. So you have to penalty. So you have this make vendor or supplier must deliver good products. Okay. Of course, when you have product oriented, lack of flexibility in product or production rates. So we are talking about mass. Okay, so you can only produce a very small variety, 1 model, 2 models, 3 models, not like job shop. Okay, job shop you can produce, you can make different kind of products according to the what they call requirement of customers, requirement requests. Also reflect no lack of flexibility in the production rates. We cannot just change. For example, this month, 2,000 units, and then next month 10,000 units. No, impossible. Because your capacity, we mentioned about capacity, right? So it depends on capacity. Okay, production rates mean how much you can produce in 1 day, and how much you can produce if multiplied by the number of days, you get your per month or per year. Okay, right. So McDonald's also have assembly lines. You see, this is an assembly line. All right. So start from number 1. Order read on the video screen. I do not know when this system, but well, in Malaysia probably we still follow this kind of assembly line. Okay, order. And bun toasting, 11 seconds, elapsed time. The time have passed. So he will, give to the second, or he himself probably will have to do it. Okay. So this is task time 20, so it will become 31 seconds. 11 plus 20. This is 14 seconds, will become 45 seconds, which is wrapping or patty with bun. Order pick up immediately to keep fresh. Okay, 45-second customer service order and payment. Right. So this is assembly line. Although it is a very simple assembly line compared to car manufacturing. Sorry, Taihen Yasashi assembly line. But of course, it depends on, because my experience in car manufacturing. So I say this is, but still, it is a very systematic. Even small, simple process must be think about this way. Then only we can do improvement. If not, we cannot do improvement. Okay. So assembly line balancing, you can see here aeroplane also have, but there is many small workstation, 1, 2, 3, 4, probably 4 workstations. Okay, 1, 2, 3, 4 stations, but not more than that. You cannot probably make a car. It's not like car manufacturing. Okay, car manufacturing can 100 cars or 200 cars on the production line. Right. So there is this method which is called assembly line balancing. So we want to balance the line. What's the objective? Objective is to minimize the imbalance, meaning the amount of waste. That means we will try to minimize the the additional time that is not used by the worker. So that's what I mean by imbalance between machines or personnel while meeting the output. So target is output, how much you want to produce. So basically, we'll start with precedence relationship. Precedence means what comes first. Precedence. What job comes first? Very simple example. If you install a car assembly line, final assembly, can you install the seat if you have not installed the carpet? Repeat the question. I repeat the question. You see in a car, there is carpet, correct? Carpet on the floor, carpet, carpet. So it's a precedence. You must fix the carpet before you fix the seat. So that is precedent relationship. What comes first must be done first, basically. Okay. So let's start with the relationship, precedent relationship. Determine the cycle time. So what is our cycle time? Our working hours and how many time actually we are going to decide, basically cycle time. Then you calculate your theoretical number of workstations. Then from there you balance the specific task to the workstation. We'll just look at a simple example. Okay, let's say this is assembling of wing component assembly. There are these tasks A, B, C, D, E, F, G, H, I. All these tasks 1, 2, 3, 4, 5, 6, 7, 8, 9 tasks. Each task requires certain time. For example, A requires 10, 11, and so on. Okay, so this is the time required. And what task must follow? So this is the precedence. This is the precedence. Okay, precedence means I said just now. B cannot be done unless you have completed A. E cannot be done until you have completed A. Right? So they mean B and E cannot be done until A is completed. So it's like this. You have A, then only you can have B, and then only can have E. Precedence. So this is time. Okay, time start 0. Okay, so you can only this until, for example, 8, 10 minutes. 10 minutes complete, only B can start. 10 minutes complete, only E can start. Of course, B will require 11 minutes. E will require 11 minutes also. So that's the meaning of that. So you can actually see all the precedents. So you need to develop the precedent diagram. Okay, the precedent diagram based on this relationship, okay, will be this. Okay, this is the precedent diagram. You can do it after the class. Okay, you can see the logic of it. It's logic. It's just logic. B and E here. C is here because B and so on. And there is time for all the work elements. Okay. Now, another thing important is this is the total time. That means if to complete this wing, you need 65 minutes. No more than that. No more than that, no less than that. You need 65 minutes. But of course, it is not 60 minutes in total. It is in sequence. Okay, it will take time to actually do it. Now I want to know work balance. Basically, how to distribute these works. Okay. So we have 480 minutes available per day. This is our working time. Working time is 480 minutes a day. Okay, let me just check so that I will not make a mistake. Okay, 480 available minutes, and 40 units is required. That means our target is actually to make 40 units in that time. Okay. So what else we need? We need the precedent, we need the time. Okay. So the cycle time, sorry about this. Okay, cycle time is given by the formula. Given by the formula. Production time available per day divided by units required per day. Okay, so 40 is coming from our forecasting or from our demand. Okay, 40 units is coming from our demand. So we have 12 minutes per unit. Okay, we have 12 units that we are going to allocate per unit. So from here, what we want to determine is the minimum number of workstations. So this minimum of workstation will also determine the number of workers, basically. Okay, so minimum number of workstation is given by the formula total time for tasks. That means the total time 65 here, 65 divided by 12 minutes per unit. Okay, so basically we want to design balance 6 stations. Okay, basically 6 stations with 6 men working on, 1 man working on each station. So we have 6 men. Of course, you cannot round up. This is 5.42. We cannot round down 5. We round up 6. Okay, so we come 6. So if you do that, okay, there is many method, okay, to allocate actually. These are heuristics or the methodology to assign the tasks. So what we'll do is just follow this, the most following task, which is choose the task with the largest number of next task or following task. So forget about the rest, okay? So when we do that, what will happen is this. So station 1 is work task A, because work task A is 10 minutes. We only have 12 minutes per station. We cannot work more than 12 minutes. So I can only assign what you call A. Okay, so that's my first workstation. Then I can assign station 2 for my B task, which is 11. So you move on, you move forward. Okay, so this will become, then it can become sequence because you cannot put B first. You should put A first because A is completed, then only B can be done. Correct. Huh? And so on. So you complete this. So the third station is actually, but of course you cannot combine this because this is, you cannot combine D and E, cannot. So this is grouped together because it is actually in sequence. So 5 plus 4 plus 3 is equals to 12. 9, 10, 11, 12. So this is my fourth workstation. Okay, this is third probably. Okay, this is third. So you see that? You see, we are trying to have the distribution. So this is now balanced. Okay, balance. I cannot have 11 workstation where if I have 11 workers, this worker will only work 5. This worker will only work 3. No, that is not balanced. That is, waste. Okay, so now we have almost balanced, which is 10, 12, a little bit, extra time for some of the stations. Okay, any questions? This is a simple example of line balancing. So imagine I have 100 stations and one station very small task, very small, smaller than this. Okay. Right. And we can calculate the efficiency, which is given by this formula, task time divided by the actual workstation time, the largest cycle time. So it's 90.3% efficient, right? You cannot get 100% efficient. Okay, that's it. This is a very simple illustration. Of course, in industrial engineering, anyone of you have been to a what do you call car factory? Any one of you? Okay, what type of production line is this? If this is my final exam question for you. Anyone can answer me. What is this? Do you think it's okay? You know, you give wrong answer is also okay. What process? What layout is this? What kind of layout is this? Okay, we'll see a bit more further. What kind of layout is this current process? Okay. This is stamping. That is press machines. Okay. Okay, stop. So just now, what kind of layout was that just now? Stamping. Huh? Please try. Please try. Anyone? Any idea?
Assembly line.
No, it's not assembly. It is actually job shop. Okay, job shop.
Job shop.
Or job shop. Okay, it is producing one particular component at a time. It's not assembly means, you know, you will see assembly after this. Okay, this is what you're seeing now. This is assembly. Okay, but it is actually some small component. The side door. Can you recognize this component? Have you ever seen this component or this in a car? Do you know where this comes into a car? Okay, what process is this? Okay, we stop here. Okay. Now, this is assembling. This is called body assembling. It is body. Karada. Karada. Body. Okay, you can see that this is actually welding shop, spot welding, and you can see the equipment that is actually being used. Do you know what these are? What these are? These things? The brown, orange color with the blue wires here. What's this? Nandaska, correct? Orange.
Robot arm. I don't know.
Yeah, robot arm and robot. It's actually a robot. Robot that actually join the parts. Okay, join the parts by welding. Okay, that's spot welding. This is spot welding, and this is a welding line. Okay. This is the side structure, and actually they put the side structure, and that is also still welding. You see how Volkswagen, they don't have men already in welding shops. They don't have workers in welding shops. It's all fully automated now. Welding shop, okay, or body assembling shop, 100% automation. So future there is no, if you workers are not going to be needed in this kind of environment of working. All robots, you see the robots moving everywhere and trying to weld the parts until it is completed. So if you see there, that is the body without the doors yet. Okay, and this is not painted body. Okay, this is still white body. Okay, white body means steel. It's steel, mild steel. Okay. Now this is the before the painting. Okay, this is they will actually do some inspection. They'll fix the bonnet. What you're seeing now is actually electro depositing of car into the ED coating. So the first coating of any car is actually first coating is electro depositing, post-fating. Okay, electro depositing first layer before they come out with second coat, final coat. Final coat is the painting. This is not painting yet. This is only the initial first layer of coat. All right.
It's not
And yes.
with color.
Eh?
It's not- It doesn't put color.
No color yet. This is not color. This is only the EDR. This is the color. That means after the this is color. This is already painting robots. Painting robots. So they will change the color. I don't know how they for Volkswagen, but in some factories they will change the color. After a certain number of runs. It's all robot. In the 80s, these are done by human beings. In the 80s, in some factories also it's still being done by human beings. But in Europe, it's already in. Okay, I'll just. I think you just follow this, because it will show every stage that is required. So imagine trying to manage operations in this such factory. Red color, okay. So you need to have synchronized. So it's very complicated and very what you call required. This is still painting. Inspection must be done by human being. Cannot. Probably there are certain things that can be done through computer or even visual system. But normally, still need. They have jump. Okay, they're putting the emblems. Okay. Sugoi ne. Hajimete desu ka? Minasan. Minasan hajimete ka? Mita koto nai ka? Oh, mita koto nai ka? So you need jig. This is called jig, so that you can have the same position all the time. This magnet actually. Okay, you just put this is magnet. Okay, so and then they put the the labels. Okay, these are. Okay, let's move it a bit fast. Okay, let's go to this assembly line. This is the machine. This is focus factory. I mentioned just now. Focus factory means there is an engine shop. So the engine shop is not connected. It's connected to the main line, but it is a separate part of the factory. Okay, it's a focus assembling of the engines. Then only they supply it to the main line. They supply it to the main production line. So they have to assemble together with you see here, this is the suspension systems, the shock absorbers that actually holds the vehicle, the car. All right. And a lot of automation, okay, a lot of right. Then this is the final assembling line. Final assembling of it's very tedious, making car. This is assembling the weather strips, assembling the wire harness. This is wire harness. We call it wire harness. A car will need a wiring system. If there is no wiring system, you cannot, connect all the electrical parts in the car. So you have electrical, units connected to the wire harness. And it must be, it's like a house, your house, you need your wiring. So it's the same thing, you need your wiring, okay? Okay, what's it? Now it is fixing, okay, it's sunroof, okay, sunroof. So you need this all these accessories, not accessories, these jigs and fixtures to help you assemble. Okay, we'll move a bit faster. And now you go to the final assembling line where you actually assemble the other components, steering wheels. Okay, too many advertisement. This is automated. Okay, this is automation in final assembling is very difficult actually in car manufacturing. So after painting, this is the final assembling. We call it final trim and final assembling. Okay, why you will see this? Why do you actually tilt the body of the car here? It used to be the worker will actually go under the car. Okay, we'll see. It's very non-ergonomics. So this is very ergonomics. The worker will just stand, direct to the car. This is not in Malaysia. It's still not being done. Okay, I don't know. I haven't seen a car assembling doing this. Okay, so this is the final assembling. So they start, like I mentioned just now, the precedence. Precedence means you cannot install the tire before you install the axle and also the brake system. The brake here is a brake. Okay, this is the brake system, right? I do not know how much you love cars, but I do love cars. Okay? Because cars is part of our daily life, not you probably. Okay, I'll just jump it further and let you see how you can see the video, by your own. But I'm just saying to you, trying to tell you that these are all related to what we have been learning for the whole semester about this topic of operations management. Okay, where you need to manage your processes so that it becomes very efficient, effective, and you can sell the car, sell the product, and it's becoming. You go to the final section, final assembly. This is the tester line. Okay, I think you have seen some of the tester line testing. Okay. They relax. I think they don't rush to work. They just, not like the other countries like Malaysia or Japan or China. We work too hard. Okay. Okay, you can see some of the technologies used to check the where is it going? If you have chance, go to factories around Japan. There's a lot of factories. There's a lot of place for you to actually see how things are being produced, how testing. This is testing the speed, called dynamometer.